everybody. Hope you're doing good. Many of you are interested in AI-driven materials design for cement and concrete, and we've developed a software tool that can do just that. And I thought I'd give you a quick overview and a quick introduction to this topic, and also show you some of the capabilities of this tool. So let's start right away. And let me just start by what this is not about. When you go through the literature, the majority of papers on the topic of machine learning in cement and concrete put it this way. You have some materials data and some validation data from the lab, and you train a machine learning model, and then you can predict the properties of new materials based on this model, right? And the focus of this is on the prediction. So people are benchmarking the accuracy of these models and have a very close look on the deviation in these predictions and so forth. So all the focus is on the right side. However, when you are designing materials, what you are interested in is this left side. So the formulation, which formulation is required in order for you to meet, on the one hand side, the mechanical and the durability properties of the material, while it's also being cheap and more eco-efficient and so forth. So the thing we want to focus on here is the left side of this equation. So how does this work? Well, basically, you have some sort of AI which gives you a prediction of a good material composition, a good material formulation. Yeah, and then you test it out in the lab. So this is not a black box approach where some AI just gives you this formulation and you have to trust it. It's much more a feedback cycle where you are getting predictions for formulations, validate them in the lab, update the model, and so forth. And the idea here is that in today's labs, the computer is barely used. Of course, you do some initial planning, maybe using an Excel tool and so forth, but all the facts are being created in the lab. And this is pretty expensive. And when we talk about concrete and cement, this is also time consuming. The reactions take place over a longer period, and especially for durability questions, this can take years until you get your results, right? And the specimens are also quite large. So you pretty quickly reach the capacities of your lab. On the other hand side, a computer is comparatively cheap. It's virtually free compared to a lab, right? Predictions can be made lightning fast, and it doesn't matter if you make one prediction or a million predictions. So you virtually have unlimited capacity. Computer-based design is not as good enough to completely get rid of the lab work, but we can reduce the time we spend in the lab dramatically. Okay, how does it work? Let's compare. So when you go to the lab, in order to find a materials formulation, what you would typically do is you would try to collect a representative sample. So say you have two parameters in your formulation that can be changed. What you would do is try to find a crit where you change the parameters in order to collect a representative sample, and then deduce from the sample the optimal formulation. The problem with that is that the whole concept of representative data collapses when the materials get too complex. So what this means is that the underlying performance of the materials can be very complex. So some formulations might work very well, such as these pink areas here, and others won't work very well, such as these turquoise areas. And if you have limited lab capacities, the chances that you hit right on these well-working formulations are pretty slim. So either you are undersampling the space, leaving out these regions, or you are oversampling a very limited region of the space by simplifying the formulation parameters, and also miss out on the potential solution, right? There is nothing limiting us from getting here in most cases, right? It's just a question of how to get there, right? And with this representative sampling, it's really difficult to end up there, especially when the materials are getting complex. And it's a bit like darting with your eyes closed. Maybe you're lucky, maybe you're not. You never know. Okay, in the AI-driven materials design, the target is not to have a representative sample of the possible solutions. The target here is to maximize the knowledge you gain. Okay, so you want to create as much knowledge about materials that work, whilst also doing as little experiments as possible. So in this example, you see you would start out at some part of this formulation space, train a machine learning model that guides you towards a promising region, collect the data, update the model, find a new material, update the data, and then iteratively search towards the optimal materials. Okay, so how does it work? This is something we call inverse design, and what I'm going to discuss on this slide is the workflow. So it all starts out by going to the lab, collecting some initial data, and training a machine learning model. This machine learning model will not be able to predict for you a formulation. Rather, it works the other way around. You feed it a lot of unknown formulations and materials. This is the so-called material search space. This contains all possible and all feasible materials. And based on your initial sample, you predict which of these materials are the most promising, right? And then basically what you do is you turn this problem into a search problem, right? You don't predict the composition. You just search for the material that has the best predicted performance. And the great thing about this approach is that the resource of your, or the source of your search criteria doesn't matter. It can be the predicted properties that the material might achieve in the lab, right? But it can also be in the known parameters, something like the cost of the material, which is often just a sum of the cost of its components, or the CO2 efficiency of the material, which again is the CO2 efficiencies of the components of this material. So once you've found a material, you can validate this material in the lab and just repeat until you find the material that you are after. So the key idea here is that through AI-driven materials design, you get very quick feedback loops that help you improve your material much faster than in a classic approach where you plan batch-wise samples, right? You try to get you try to draw conclusions from these samples and then improve in the next iteration. And this takes much longer. Whereas with this AI-driven materials approach, you can be much quicker. How much quicker? Well, we benchmarked this in various scenarios on a number of data sets and published it in the Journal of Cleaner Production just this year. And we came up with an improvement of up to 40 times compared to the classic screening approach. While this gives you a good idea of the capabilities of this approach, of course, it's an abstract number. You wouldn't do just the same thing, but 40 times quicker. Instead, it enables you to solve problems that are much more complex, problems that are currently out of reach for a normal buildings materials lab. For instance, When you look at the resources we have as alternatives to these cementitious materials, they scatter a lot. So their composition can vary depending on many factors that we cannot control. So using these as a resource is very risky because you never know whether or not the base material is reactive enough, if it's going to work as your cement supplementary material. So what you can do instead is, instead of just relying on single sources, you can spend this search space where you try out all possible combinations of resources and then opt for the regions where the materials work very well. So you are not reliant anymore on having just one good resource stream, but you can combine various resources to find a matching material. Yes, and this is what this approach enables you. So basically find a fine-tuned composition, which is more complex than your classic building material, but which works every time. So in the next part, let's have a look how this works with our software tool. It's being deleted. So there's no other database in the back. We don't have access to what you put in there. Everything is stored in a session, but you can save sessions and upload sessions again. So basically, this tool is divided into two main parts. One is the digital lab. This allows you to create a digital representation of all your base materials and processes that you have available for your materials, and then create you these search spaces. So it's not exactly easy to write down hundreds and thousands of concrete formulations. So this part of the tool here is there to aid you in this process and to let you create all of these formulations with a few simple clicks. And then you have this materials discovery module, which you can use to search through this design space according to your requirements. I want to also emphasize that there's a user manual, which describes in great detail the use of this tool. There's also throughout the tool info boxes that tell you exactly what is required as an input here. So, but let's start with the basic workflow. So the idea here is that you create a digital twin of all the materials that you have available, and these then serve as the input for your formulations that can then be created automatically. So let's start out here. I have prepared some files, a session. You can also download these data. Link is again in the description. And just select this session complete JSON file, upload it, and you will see the same materials appearing on your screen. So if we want to run a materials design project, right? These might be all the materials we have or we want to use for our recipe. We see here fly ash, ground granulated blast furnace slag, water, pure water, fine aggregates, coarse aggregates, and so forth. All these materials have been created using this form. Again, the gray box explains exactly what you are supposed to do here. So basically you select powder, liquids, aggregates, admixtures, or a process, or something custom. And then specify the name, let's say cement, right? And you can add properties such as the CO2 footprint. Let's say 500 kg per ton costs, I don't know, 80 euro per ton, right? You can also add composition features such as the molecular composition, or better said, the oxides of this powder or structural information such as the fineness of the powder. But you can also add custom properties. So in case the forms do not contain the properties you are most interested in, you can add the properties here, yeah, such as the color as a custom property. You can just click submit, and then here in this list, in this table, you see cement appeared and now is also part of your digital lab, and you can use it later on. If you want to edit it, just click the pen symbol and you're able to edit all the information you might have missed out or add more information. Okay, let's delete it. We're not going to use cement. We're going to look at alternative materials here only. Okay, so once you have these materials specified, again, you can not only specify powders, you can also specify liquids. Then these composition features change depending on your selection, right? There's a special form for all materials. Once you've created all the materials you need, powder, liquid, aggregates, and maybe admixtures, you can blend materials. So what does it mean? Let's say you want a powder blend, right? Give it a name, select powder as material type, select base materials you have available, and then blend them using the blend form. So basically you can say, I want a 50% fly ash, 50% ground granulated blast furnace slag mix, and it will, you only need to fill in one, it will fill out the others automatically, right? And you can say you want another blend that is maybe 30% fly ash, 70% ground granulated blast furnace slag, or 75, right? You can also add an increment. This basically refers to having various intermediate blends of these materials. So for instance, if I put in here, right, it will create blends of 50. If I put in here 5% as an increment, we will have a 50-50 blend, a 55-45 blend, a 60-40, 63-35, and so forth, right? You can add blending ratios manually. You can delete blending ratios that you didn't intend to create in the first place. And once you're done, you can submit these materials and in this way create new materials that are based on your base materials. Like for instance, in this case, blended aggregates, which are a mixture of the fine and the coarse aggregates, or an activator liquid, which is a mixture of various components of this liquid, or a fly ash GGBFS blend, which is a powder blend consisting of fly ash and GGBFS at various levels. Okay, so basically you've created your base materials, you've created a blend of materials. Now it's time to create formulations of this. What you have to do is select if you want to create a concrete formulation or a binder formulation. The difference between the two is for concrete, you will need a powder, you will need a liquid, and you will need aggregates. Admixtures, custom materials, and processes are optional. For binder, on the other hand, you're free to choose aggregates. You don't have to choose aggregates if you want to define a mortar. Of course, you can also add fine aggregates here. Okay, so only difference is different material models. But let's create a concrete, which consists of various fly ash GGBFS blends, an activator liquid, the blended aggregates, an admixture, and as processes different curing treatments of the mix. Let's also add the weight that we are after. I'm gonna just put in 2,400 kg of concrete, which is equivalent to 1 cubic meter of concrete. You can give it a name, right? The data set, and let's create all the formulations. And you don't have to create each formulation manually. Again, you can just define the range of numbers in which your composition is supposed to end up, right? Maybe 350 to 450, and by how much it shall be varied. For instance, 10. So now it counts up 350 kg of powder, 360, 370, 380, and so forth, all the way to 450. Same goes for the water cement ratio. So you can start out at 0.4, go up to 0.6, and all of this at an increment of 5%. You can also add admixtures at various degrees. You can say at an increment of 2, change it between 10 and 12. Yeah. And then what it will do for you is, given these ranges and these increments, create for you all possible combinations of these materials, right? So these are just the weight fractions. You see 350, 140, that's the powder and the liquid respectively. 10, this is the admixture, and the rest is just filled up with the aggregates. And the sum of these weights will be 2,400 that we specified early on. So now that we have all the different possible weight fractions, we can click on create material formulation for this given configurations. We can also edit some, we can delete some. And what it now does is it accesses the materials that we have represented earlier. It uses these weight fractions and automatically calculates the properties for all of these materials. So now we created, with a few clicks, hundreds and hundreds of materials formulations with different weight fractures, different precursor materials. And all these materials occur here, and they can be your search space for later AI optimization. Okay, so this is how you create a search space using SLAMD. What happens next is you can submit this material search space, and now it will be available in the discovery module. In the discovery module, this is where you specify all your requirements. Let's have a look how this works. So what we see here is the test CSV. This is the material search space we just created. We can also upload our own CSV files with a material search space that has been created, maybe using an Excel tool or a Python script or whatnot. So the first step would be to go to the lab and test out some examples from the search space, and then add this data, for instance, by using this add target button here. So we could, for instance, add the compressive strength after 7 days, okay, in megapascal. Click on add target, and now a column appears for each formulation where we can put in what we have just measured in the lab. I'm going to put in arbitrary numbers now, yeah, but basically here you can just put in the numbers you've measured. And now your data set is available, your training data, and you can start the search process. So I've prepared a training data set from the literature. This is also in the example files you have available. And you can select this discovery example, and it has a huge benefit of already having some training data in there. And we also know the outcome of all the other results. Okay, so let's just upload this file using this select file dialog. Click on the discovery data example, click on upload, and then upload dataset, and it appears down here. Next step is to select this file. Select all the formulation parameter on the left side here. So the index is just the number of the formulation. This is not a formulation parameter. Powder kg, liquid kg, water to cement, the oxides, LOI, fine parts gravity, the activator liquid, all of this, temperature, the duration of the curing, all of these are parameters of the formulation. And then select a target, and this target is what you want to, basically what's your requirement. Let's not go too deep. Let's just click on this Run Experiment button and have a look what we end up with. So basically what we see here is the predicted outcome of the formulations in our data set, right? So these are all the formulations that we have not yet validated in the lab. And this predicted outcome is mapped to a measure which is called the utility. This is also shown here in colors, right? And in our case, we specified that we want to maximize our 28-day lab validation strength, okay? So a higher utility is for materials that have a higher strength because we selected maximize. We can also say we are only after a material with 40 megapascal. So what happens now is that materials that have a performance that is predicted higher than 40 megapascal all get the same utility. So there's no advantage in having a higher strength anymore because you specified that 40 megapascal is enough. Okay, but there's more. We can also, for instance, select the CO2 footprint. If you've created this design space with SLAMD and you've put in the CO2 footprint as in the base material, it automatically augments for you all the CO2 footprints, costs, and so forth for each formulation. So we can use this now as an optimization criteria. We don't have to predict it. We can just calculate it based on the information given before. So we select it in this box of a priori information. CO2 footprint, of course, we want to minimize. Let's run the experiment again and see what happens. So now we see here the trade-off between CO2 footprint and strength. And what we see there is that the higher the strength and the lower the CO2 footprint, the higher the utility. So this utility really is a tool for you to formulate really complicated requirements on your material with one number. And the number that has the highest utility is the material that is best suited. Okay. Let's add another one. Let's add the costs, for instance. Again, something that we can just augment. We don't have to predict it. Let's do the experiment again. And now what we see is the trade-off between costs and strength, as well as CO2 footprint and strength and costs and CO2 footprint. And this complex matter is broken down into a single metric, which is the utility. And the higher your utility, the better the material is suited. Okay. So this is how you formulate exactly your requirements. You can also say you're only interested in materials that are cheaper than $100 and have a CO2 footprint below 100 kg, and then it automatically filters out all the materials that are not suitable and narrow down the search problem for you. Okay. But let's keep it simple for now, because I also want to show you another very helpful tool. Let's just say we want to maximize our strength of the material. Then we can make this selection, select strength, click maximize, run the experiment, train the model basically, and then look at this plot. So this plot is an abstract mathematical plot. It's called a t-SNE plot, and it basically is a map of the composition of your materials. the coordinates have no real meaning, right? But you see that these, I think it's 240 points are clustered here according to the composition of the materials. So we see 3 clusters for the 3 different powder plants, right? With high fly ash content, lower fly ash content. And each of these clusters is split in 2, one for heat curing, one for ambient curing. And we also see the training data we have already collected. So somebody already put a lot of work into this and used 10, I think, training data points. And now we can make predictions to all of these other material plants. And the nice thing about this is that this can be really helpful in the selection of the next material. So naturally, we would choose the material to validate next that has the highest utility, which is this material over here. And maybe we want to do 4 experiments. So we can also select another material, and we wouldn't select the one that's right next to it because this is basically a very similar material. We would look out for all the other materials in this data space. Okay, so we could select this guy, but we could also say, what about the curing? What is the influence of the curing? Let's select a data point here, right? And this way, add through only few validations in the lab, a lot of information to our current existing data set, right? So here we have all the variations with a certain fly ash and GGBFS blend, and we can make sure that we are selecting the one with the best water to cement ratio, with the best powder content and the best composition overall for our purpose in maximizing the strength. Okay, so let's select these 2 materials. How does it work? It tells us row number 1, row number 2. So we scroll down to this table, which shows us the utility. So all the materials here are sorted according to the estimated utility. And it shows us the lab validation. So this is the predicted value of the strength, right? It also shows us an uncertainty of this prediction and the composition of the materials. So here we see material with the index 17 and the index 177 accord to these 2 candidates here. Okay, so let's go to the lab very quickly, create these materials according to these formulations. Can also just download our predictions, and we have an Excel table of the predicted outcomes. Go to the lab, validate the materials, and add the results here. Fortunately, somebody already went to the lab, and we can just take their results and fill it in. So formulation 17, 60.18, that's a high strength material for sure. Let's look at formulation number 177. Okay, so here we have 37.52, completely different result compared to the first one. So let's just add these 2 samples and see how the utility of materials changed after adding this small number of data points here. And what we see now is a completely different picture. So first we had these training samples in the middle, right? And this group of materials and this group of materials basically was predicted to have the same, more or less the same properties. And now we see by just adding 2 data points, we know that this material is a lower strength material. It's not interesting anymore. So we can focus on these materials. And could, for instance, select another data point from the heat curing group of materials, the one that has the highest predicted utility. I think it's minus 0.91 is the best candidate over here, row number 36. Note that this is not the one with the highest utility. The experiment with the highest utility would be this guy, which is probably very related or very similar to this experiment. So adding this point would not create so much new knowledge. So you see, this map is a nice tool in order to maximize with only few experiments what you can know about these materials. And we already learned so much from just adding these two materials, and look at all the effort that has been done before. And just adding two more can really give you a much better understanding of various formulations. Okay, let's add row number 36 at the end. So if we go here, row number 36 has a predicted strength of 42. And it's material 57. So let's see what the actual performance of this material will be. Let's just go to number 57. Look up what somebody already validated in the lab. Oh, 64.6. So again, a good choice adding this sample to our data set, because now we learned that the heat treatment can be really helpful in order to increase the strength. Let's have a last look at our map. And boy, did it change from what we knew when we did the systematic data collection at the beginning to what we know now by just adding 3 data points. And I think that's the magic of using this approach, is gaining knowledge about the materials super quickly, make sure that out of all the possible variations of the compositions, you've identified the ones that are most promising very quickly. And I think now, after just adding 3 more experiments, you're ready to design a really cool material with exploiting all the knowledge you have from the data collected. And basically design a material that is on point with your requirements, be it in terms of the strength of the material or the costs or the CO2 footprint. So I hope this quick introduction to the app was helpful to you. Let me know if you have questions in the comments of this video. You can also always reach out. If you want to get in touch, just go to the start page, visit our website, visit the GitHub repo, where you find all the source code. Again, this runs under an MIT license, so please feel free to use it for your purposes, commercialize it if you want, use it for scientific purposes, and do great things. So thanks for your attention. See you guys all very soon. Bye-bye.